Hello, everyone, and welcome back to another exciting episode of Math Homework with your favorite professor, Professor Tony. So, we're going to be looking at sections 8.3 and 8.4 for this video. I decided to bundle them together because there weren't that many questions for either of them, and they're mostly using your favorite phrase, which is use technology. So we're going to just go through a couple examples on how to do them and make sure they aren't, troublesome. So we'll start with this one because I think it's the most wordy out of 8.3. So they tell us in a test of effectiveness of garlic for lowering cholesterol, 81 subjects were treated with raw garlic. Cholesterol levels were measured before and after the treatments. So the changes, which were the before minus the after, in the levels of the LDL cholesterol have a mean of 0.1 and a standard deviation of 2.07. They tell us to use a 0.01 significance level to test the claim that with garlic treatments, the mean change in LDL cholesterol is greater than 0, which would be no change. So what do these results suggest about the effectiveness of garlic as a treatment? And then assume that the sample is a simple random sample and identify the null alternative hypotheses, our test statistic, our p-value, and state a final conclusion about the claim. So right off the bat, we're testing the effectiveness of garlic for all of these patients. So we're going to set up our hypotheses as our null hypothesis being equal to 0 because that's our threshold. We just want to see a change. So they have to have a mean more than 0. So alternatively, for our alternative hypothesis, we're going to have our mu being greater than 0. So that's why we choose, well, for me, it's part D for our correct hypotheses. So for the next part, they want us to determine our test statistic and our p-value and then state the final conclusion. So to calculate the p-value and the test statistic, we want to pull out the information we know, which the problem kind of gave us a lot of information, but we want to pull out the important pieces. So starting off, they told us we had 81 subjects. So we know our n is equal to 81. They do tell us that we have a mean for our sample of 0.1. So remember, anytime we're dealing with our samples, we're using our English letters. So we'll have our X bar, not our mu, because our mu is talking about our population. We know the information just for our sample. So we're going to use X bar to denote our mean as 0.1. And then they tell us that we have a standard deviation for our sample of 2.07. So again, because we're dealing with our sample, we're going to be dealing with our English letters. So we'll use S. We'll use S to denote our standard deviation, which is 2.07. So they also tell us that our significance, or our alpha, is going to be 0.01, which we'll use later to find or to create our conclusions. So for now, we do have to use this information. So we know that we have a formula for our test statistics when we don't know our sigma, but this problem also doesn't give us a mu beforehand for us to measure. So we're going to have to use technology to find our test statistic and our p-value because we weren't given enough information about the before. So I've already opened StatCrunch, so let me close out of that. So remember that anytime you need to use StatCrunch, you can go into question help, and StatCrunch will be listed here for you. So once that opens up, I'll just smooth this over a little bit, hopefully. And it's going to take forever to load. All right. So now that we have some of our information that we can use, we know that since we don't know our sigma, we're still going to have to use our t distribution to measure. So we can go to stat and then go to t-stats. And we only have one sample and we only have a summary. We weren't given a list of data points, so we know we're going to have to use summary. So now we'll be prompted to enter our mean, standard deviation, and size for our samples, which is always important to note that it's always talking about our samples. So our sample mean is our x bar, so 0.1. Our sample standard deviation is what we put as our S, so 2.07. And our sample size is just the number of people, which we had 81 participants. So once that portion is all filled in, we can move on to our hypotheses. So we're testing our mu. So our null hypothesis, we have equal to 0, which is the same as our problem. But we want to make sure that we change our alternative hypothesis so that it shows our mu being greater than 0 because we're looking for a change. So once you have everything matching what we've already selected in our problem, we can continue. And if we hit compute, it'll give us our test statistic here and our p-value here. And it's always important to note, make sure you're rounding to the correct number of decimal points. I know sometimes that's something that trips you guys up, so just make sure you're double checking. This one wanted 2, this one wanted 3. So once we've made it that far, we've got everything filled in, we're just left with stating our final conclusion. So what's important about our final conclusion is that we want to be comparing our p-value to our significance level or our alpha. So if you guys remember from the cheat sheet, if your p-value is less than or equal to your alpha, you reject your null hypothesis. And if your p-value is greater than your alpha, you're going to fail to reject your null hypothesis. So our p-value is 0.332 and our alpha is 0.01. So clearly our p-value is greater, and when our p-value is greater, we fail to reject our null hypothesis, and that's telling us that there is not sufficient evidence to conclude that the mean of the population of changes is greater than 0. So that didn't show significant evidence that the mean change is greater than 0. And that's just how we phrase our final portion. All right, guys, so moving on to the last problem in homework 8.3. So I wanted to choose this one because it was a little different because they're actually giving you data to find out more about the problem. So for this one, they tell you a group of students estimated the length of 1 minute without referencing to a watch or clock, and the times in seconds are listed below. And they want us to use a 0.05 significance level to test the claim that these times are from a population with a mean equal to 60 seconds. So we want to see how closely they can guesstimate 1 minute. And then it goes on to say, does it appear that students are reasonably good at estimating 1 minute? So we want to see if they can guess 1 minute or 60 seconds or not. So for our hypotheses, we're going to solely be looking if they can guess it or if they can't. We don't want to know if they can guess less than 60 seconds, if we can guess more than 60 seconds, we're only looking at 60. So we're going to be setting up our null hypothesis to be equal to 60 and our alternative hypothesis to be not equal to 60, sorry. So to do everything that we've been doing before, clearly we don't have information about previous trials or anything like that. So we're just going to have to solely base everything off of the data that we're given. And because we don't know our sigma, which is our population standard deviation, we're still going to be using t-statistics to calculate everything. So if we click this window, make sure you click this one so that we can export our data. And we just want to open it in StatCrunch. And hopefully it will open quickly. All right, so we now have our list exported into StatCrunch. So we can go up to our stat selection, go down to t-stat. We only have one sample and we're dealing with data. And remember, we're dealing with our t-stat because we don't know our sigma, which is our population standard deviation. So if we select with data, hopefully it loads. My computer has been so slow. I'm sorry, guys. All right, here we go. So we want to make sure we select our variable column. We don't have to worry about where or grouped by. We just want to next focus on our hypotheses. So we want to make our hypothesis match what we decided our hypothesis was in the beginning. So we're looking to see if we can average the students guessing 60 seconds. So we want to change our hypotheses to 60. And alternatively, we're looking to see if it's 60 or not 60. We're not looking for less than or more than, just if it's equal to or not equal to. So we don't have to change this one. So we're all set and we can just select compute. So once it's computed, you can find your test statistic and your p-value here. And then we can move on to our final conclusion. So remember, we're going to be comparing our p-value to our alpha. So if our p-value and our alpha, our p-value was 0.585 and our alpha was 0.05. So clearly, again, our p-value is greater. And remember, anytime your p-value is greater than your alpha, you're going to fail to reject your null hypothesis. And if you're ever unsure or you're forgetting, remember that this is part of the cheat sheet I posted in the chapter 8 lecture section. So if you are unsure and aren't sure what to do, it's always good to consult the cheat sheet. So we want to fail to reject our null hypothesis and then move on to look and see if there is sufficient evidence to conclude that the claim that the mean of the population of estimating 60 seconds is or is not correct, and if it appears that as a group the students are reasonably good at estimating 1 minute. So depending on the values you get, you want to compare them to the full sentence and make your conclusions off that. So the last thing I want to go over for section 8.3 is actually number 2, because I forgot to do it, initially. So for this problem, they give you a claim that smartphone carrier data speeds at airports. They give you the mean, the sample size, and the test statistic, and then ask you to find the p-value, which is different from what you're used to seeing. So typically, back in my day, we would use a calculator for everything because we didn't really learn in Excel or we didn't have StatCrunch as an option. So my typical method would be to teach you how to do this in a calculator, but it's no longer as applicable as it used to be as an option. So instead, we're going to be looking at using online resources. There are a multitude of online calculators and resources that you guys are now have available to you that I did not, at least for the most part, up until recently. Now I have more access to these things. So I've looked around and I found some online calculators that should be more helpful from this point on. So I'll just show you an example on how to get there. So we have this problem. They've given us our test statistic for t and our sample size and a mean. So typically I would use a calculator, but I know most of you don't really use a TI-84 or even have one. So I figured I would show you an alternative. So I'm gonna give you a link to this calculator. It's called GraphPad. Well, it's a section of GraphPad. And it's actually a p-value calculator based on any of the information you have. So we can do z, we can do t, we haven't talked about f yet, or r, we can do those too, or we can do chi-square, which all of these, with the exceptions of f and r, should be fairly familiar to you. So we were given in our problem a sample size of 22 and a t-score of 1.756. So our degrees of freedom would be 21, because it's always just n minus 1. And our test statistic, we can just enter. So if we go to our t section, it was 1.756. And our degrees of freedom was 21, because it was just the 22 minus 1. So we can hit compute. And so we can see that it gave us our p-value for a two-tailed expression, which we don't know anything else about the expression. So we can base it off of that and just make sure you're rounding to the correct number of decimal places. So an online calculator is a great resource, and I always encourage you, if you know how to use technology, definitely do it. But for the time being, I'll give you this link, and if you ever need to double check your work, this is a great way to do it. All right, guys, so jumping right into section 8.4, there are only about 4 problems that require long drawn out answers. So I figured I would do 1 or 2 of those. So I'm starting just with number 1, and they tell us a simple random sample of 41 men from a normally distributed population result in a standard deviation of 7.4 beats per minute. The normal range of pulse rates of adults is typically given as 60 to 100 beats per minute. If the range rule of thumb is applied to the normal range, the result in a standard deviation of 10 beats per minute. So you don't have to do the range rule of thumb calculation. They do it for you, which is nice. So they say use the sample results with a 0.05 significance level to test the claim that pulse rates of men have a standard deviation equal to 10 beats per minute. So they gave you your definitive answer for how to phrase your hypotheses. And then they want us to complete parts A through D. So because they told us here that they want our pulse rates to be equal to 10 beats per minute, we're going to be looking for it's either equal to 10 beats per minute, or alternatively, it's not equal to 10 beats per minute. So also, I kind of wanted to point out that sometimes they'll use a 1 for your alternative hypothesis or an A. You can use either one, whichever one you like more. Just always remember that you can see either of them. They mean the same thing, but your null hypothesis will always be a 0. So just something to keep track of, making sure you're staying with me. So let's pull out what we have. So what we know is we have an N, or total number of people, as 41. And they tell us that we have a standard deviation for our sample. So we're going to use an S as 7.4 beats per minute. And they gave us our range rule of thumb, which we used for our hypothesis. But other than that, the only other piece of information they really give us is our alpha, which is 0.05, which we're just going to use to compare to our p-value. So this isn't really a lot of information, but don't fret. We don't really need a lot for our standard deviations because we're just measuring how far they are from the mean. So there is a way to do this on the calculator, but I think it's more effective to show you how to do it in StatCrunch. So StatCrunch only has an option to use variance. So if you remember the relationship between variances and standard deviations, your variance is just your standard deviation squared. So if we were to take s squared, it would give us our variance. So if we took 7.4 squared, it would be equal to 54.76. So our variance for the problem would be 54.76, which we'll need to use if we want to use StatCrunch as opposed to using a calculator. So I'm just going to write that down here. If my Apple Pen will cooperate, there we go. As 54.76. That looks much nicer. All right, so just remember that that's where I'm getting my variance from. All it is I'm squaring what I already had. So we can also look at our hypotheses. So if we're scaling our standard deviation, we should probably also scale our hypotheses. So just for the sake of thinking about it in terms of a variance as opposed to a standard deviation so that we can use our calculator, we'll be looking at if it was 10 squared beats per minute. And 10 squared is just 100. So when we're plugging in, we're going to be using 100 as our hypotheses, and that's just because when we're dealing with a variance, remember the relationship between a standard deviation and a variance is just this square. So the only difference, I'm just going to say it again, I guess, the only difference between standard deviation and variance is that you square that number to make it into your variance. So all we have to do to be able to use the variance calculator is square the information we have. The only thing we don't square is our number of people. And that's because our sample size hasn't changed. It's just we're squaring the outputs that we're getting from that specific sample size. So we don't change our sample size, we only change our sample standard deviation and our hypotheses. So I'll show you how to plug that in now. I just wanted to go over that in a little bit more detail just to make sure it wasn't too confusing. So if we go up to stat, like we have been for this chapter, you'll notice that there isn't a standard deviation stat, but there is a variance stat. So because we know the relationship between variance and standard deviation, we can use variance stats, one sample, and we have a summary. So we can click that. So all we have to input is our sample variance and our sample size and our hypotheses. So our sample variance is what I calculated down here. It's just our sample standard deviation squared. So the 7.4 squared, which was 54.76. So we can just put in 54.76. Our sample size, remember, stays the same because our variance and our standard deviation are based off of our sample. So our sample size stays the same. But because we're squaring our standard deviation, and because we're measuring our standard deviation, we also want to make sure we square our hypotheses. So even though we had 10 here, we're going to be looking at 100, which is 10 squared, here. So once that's all filled in, we can hit compute, and it'll give us our chi-square statistic and our p-value. So I know this is kind of a strange method. Usually we can just put in the numbers we get from the problem, but because we don't have a standard deviation option, we only have variance, we have to kind of work with the tools we have, and since we know the relationship between the two, we can manipulate the data just a little bit. So once all of that is filled in, we can do what we've been doing before, compare our p-value that we calculate against our alpha, and we actually have a scenario where our alpha is larger than our p-value. So we get to reject our hypothesis, and then the remainder you have to look at based on your specific scenario. All right, guys, so this is going to be the last one I'm going to go over just because this is an example of when you have really small numbers and when things can start to get a little dicey. So for this one, we are measuring piston diameters of a certain hand pump in 0.08 inches. So the manager determines that the diameters are normally distributed with a mean of 0.8 inches and a standard deviation of 0.006 inches. And then after recalibrating the production machine, the manager randomly selects 23 pistons and determines that the standard deviation is 0.0052 inches, as opposed to the 0.006 before. So is there significant evidence for the manager to conclude that the standard deviation has decreased at the alpha, or significance level, of 0.10? So now we want to set up our hypotheses. So what we're testing for is that the machine has a certain calibration. So we want the mean size to be 0.8 and only have a standard deviation of 0.006 inches. So we want to set up our hypotheses to match that, because we want to base it off of the entire population of piston diameters as opposed to just what we randomly selected. So you want to make sure you're pulling out the right information for your hypothesis. So for our first hypothesis, we want to test that it's equal to our allowable standard deviation. So for me, 0.006. My pen is not writing. All right. All right, sorry about that. Technical difficulties. So we want to make sure our null hypothesis is set up to be equal to the maximum allowable standard deviation. And alternatively, we want our widths for our piston diameters to be less than that standard deviation, because we want everything to either hit that calibration or something less than that, because we never want things to vary more than that. And that's all the standard deviation is measuring. So our alternative hypothesis will be that our standard deviation will be less than 0.006 to create a better product. So moving on to calculating our statistics. So we have a little bit of information on this one. So we could calculate it out by hand, which is probably a good thing to do just to show you that how much fun it can be. So if we pull out the things we know, we have our population standard deviation, or the correct calibration, as 0.006. We also have an N of 23, because you know in our sample we're measuring 23 of these individual pistons. And for those 23, we measured a sample standard deviation of 0.0052. So if you're ever looking to calculate your standard deviation by hand, we can always use the formula x squared is equal to n minus 1 multiplied by our sample standard deviation squared over our population standard deviation, or sigma, squared. So we can just plug in. We know our n is 23, so 23 minus 1 multiplied by our sample standard deviation, which is 0.0052 squared over our sigma squared, so 0.006 squared. And it's always important to remember your squares because those can drastically change your expressions. So we could calculate here our x squared value to be around 16.524, which is the same as what you would get from your digital output, which I'll show you in a second. And if you calculate your critical value this way, remember you can use the GraphPad calculator I just showed you previously. Let's see if it's still open on my computer. But let's see if I can go there really quickly. So we're going to pretend I didn't write all over my screen. And you'll see that there's a chi-square option with degrees of freedom. So we'll plug in this chi-square we just calculated, 16.524. And our degrees of freedom would be 22. We can hit compute. And you'll notice that they give us a p-value of 0.7891. But if we take 1 minus 0.7891, we'll be left with 0.7891. You'll be left with 0.2109, which if we round would be 0.211, just like our digital output, which is what I have over here. So that's how you could do it by hand, or mostly by hand. I guess you still have to use a calculator. But let's also look at how we can do it in StatCrunch. So like we talked about with the previous problem, when you're using StatCrunch, we only have an option for variance. So I want to clear some of this. So if we're just looking at our variance, that means we have to start squaring some of our values. So we want to square our sample standard deviation and our population standard deviation, but we don't need to square our n because we're still dealing with the same number of pistons. It's just we're squaring our standard deviations. So we just want to take our sigma squared, which would be 0.00036, and our sample standard deviation would be 0.00002704. This is when it starts to get complicated, when there's a lot of zeros. So you just want to make sure that you are calculating all the correct numbers of zeros to make sure your numbers will be accurate. So we can go up to question help. and open StatCrunch. Close this a little bit. So we'll go like we normally do to stat, the variance stats, one sample, and we have a summary. So we want to enter our sample variance, which would be our sample standard deviation squared. So this bottom number. So 0.00002704. I know it's a lot of zeros, but we know our sample size already. We only took out 23 pistons, so we can just enter 23. And then we want our hypotheses to match our sigma squared. So we'll change it, instead of putting in 0.006, we have to put in 0.006 squared. So 0.000036. And then we want to make sure our signs are correct. So we want our sigma to be less than our alternative hypothesis. So once everything is set up correctly and you double check your numbers, we can hit compute and we'll get the same outputs that we just got from doing it manually. So remember, doing it manually is always an option. You don't have to do it that way. You can always use technology, but always remember that sometimes it is easier to use actually the handwritten formula. So I hope this was helpful for you guys, and I'll talk to you all soon.